The concept of the derivative has a geometric interpretation. It is a slope of a curve. The physical interpretation is an instantaneous rate of change. In calculus, these two perspectives are the same. The founding fathers of calculus in the late 1600s, Isaac Newton and Gottfried Leibniz, raised a fundamental question. What is the instantaneous rate of change of something? Say this in terms of, how fast is Usain Bolt going right now? What is happening in this instant? This is the instantaneous rate of change. The derivative of a function measures the change in output value with respect to a change in input value. For example, to measure how quickly the position of an object changes when time advances, an object's velocity is a derivative of the position of the moving object with respect to time. The derivative of the function is the slope of the tangent line to the graph of the function at that point. A tangent line is not merely a straight line touching a graph at one point. It essentially provides the best linear approximation of a function at that one point. Therefore, this statement further defines to be the ratio of the instantaneous change in the output with respect to change in input.
To find the gradient of a line, you would take the coordinates of 2 points and apply the rise over the run, and the same applies for finding the formal derivative using first principles on a given curve. To find the rate of change, which is delta x over delta y, and to derive the formula, you would use the points on the graph shown, which is the same as the rise over the run form. The x values for the first principles are x and x plus h, where h is positive. And for the y values, fx and fx plus h. This doesn't help very much until you apply the limit of h heading towards 0. As the gap between the 2 points gets smaller, it provides a more accurate representation of the slope changing instantaneously. The formal derivative represents the instantaneous rate of change by showing the gradient over a period equal almost to 0, allowing for an almost exact gradient to be given at any point.
The derivative of a function is to obtain a value for the rate at which y is changing due to a change in x. The derivative of a function is written as f-x. We can find the instantaneous speed at which a radioactive compound, arsenic-74, is decreasing in size at any point in time. The half-life of the compound is 17.5 days, so the exponent of the formula will be t over 17.5, where t is the number of days. Assuming we started with 100 grams, the function for the amount of remaining arsenic in grams will be equal to 100 times 0.5 to the power of t over 17.5. Say we wanted to know the rate at which the compound was decaying at t equals 20 or 20 days into the decay. We will use the first principle described in part 2 to approximate this figure and then check it using technology. All we have to do is shrink h to a small enough value for an accurate approximation and fill in the formula. This means that at t equals 20, the mass of the compound is decreasing by 1.793713 grams per day. This is an instantaneous speed, so clearly the rate will be constantly changing for any function that isn't linear. When this is checked using technology, we get an extremely close answer.
We use the first principle, fx plus h minus fx over h, and check the answers using technology. Also from the previous graph, we saw that the rate of change is decreasing as the mass of the compound falls. Some comment on any social, environmental, and or ethical implication. The reason we will want to find the speed at which the compound is decaying is to accurately approximate the amount of the materials remaining after transport to a hospital for use. Arsenic-74 is used to locate tumors in the human body. The compound is only useful in certain quantities, so that it is imperative to know how much will be remaining after a given period of time of transport. Another use of finding the rate of change of a decaying radioactive compound is to calculate how long before radioactive waste from a nuclear reactor has to be stored before it is no longer harmful to the environment.